colleagues, good morning. We continue lectures by Marcin Moszyński. Please.
This is the next part, number 4. I would like first to recall some notions from the last lectures. M is our matrix measure on sigma algebra M also, but Gothic M in omega. The omega is the whole set. Soon our omega will be the set of real numbers, but now it's general. And we defined... I don't hear. Звук плохой.
Разговаривать по сотовому с Никитой, а вы здесь слышите, о чем они говорят. Продолжайте.
Да? Хорошо. No, our main Hilbert space is capital L2 M space, but we also consider this, we can say, semi-scalar space, which was necessary to construct our main Hilbert space. And this is Hilbert. This is not the Hilbert space, but this is just semi-scalar product space of functions, and the elements of our Hilbert space are not functions, but classes of functions. So, instance f, g. So these are classes from this space, and I can recall that also that the class f consists, this is a layer which is obtained by f plus the zero layer, which was defined. I will not recall this, I hope you remember. But this is a special subspace of this space, which has the semi-norm equal to 0, just. Yes. The semi-norm obtained by this semi-scalar product is just 0, so this form a linear subspace, and this is the form of each element of F. So this is a the standard construction, similar to the construction of L2 spaces for measures, just for measures. But for measures, we usually do not distinguish between this and this by tradition. And here we distinguish everything because this is quite delicate. It's not good to think about those elements as about functions. It's delicate. Okay. So now I would like to tell something about multiplication operators. It will be important for us because you remember that for our main theorem we would like to prove in the general case, formulate and prove in the general case. In our simple case, we can say we just proved that the cyclic self-adjoint operator is unitary equivalent to an operator in such a space, in L2 for the measure, to the operator which was the multiplication by the function x the identity function. And we would like also to consider such kind of operators of multiplication by functions in subspaces. So the definition would be very similar, and also properties would be similar, which is quite convenient. So consider first function f capital from omega to c, its scalar function, and measurable with respect to our sigma algebra. And the multiplication by f operator will be denoted similarly as in usual L2 of measure spaces like this, and it will be defined as follows. So first, the domain. The domain of this operator, it will be in some sense a maximal domain, which can be taken for this operator. So we consider such classes belonging to our space that when we take the product, just a product of a scalar function and the vector function, because f is a vector function, as this is a scalar function, so we can multiply and we can take the class. Or we can say, okay, we can say like this, just to make the sense. This has sense every time, because this is a function, and we can, this is a vector value function, and we can just ask, does it belong to this space or not? And when it belongs, it's okay. So we are in the domain. Yes. So this is the domain, and of course, when we have an element from the domain, so for f which belongs to the domain, for the class of f which belongs to the domain, we define Tf on this class just as the class of this. So this is the definition. And of course, it's easy to check that this is a linear, the domain is linear and the operator is also linear. It's trivial. And of course, we should check something which is also trivial. We should check that this definition does not depend on the choice of f. Yes, but so to do this, we should recall what does it mean belonging to this zero layer. So I can do this now. So it's enough just to check that when we take f from zero layer, that f times f capital times small f also belongs to zero layer. Yes, this is our question. If this is true, it's okay. Yes, by linearity, which is trivial. So, by linearity of this multiplication on this level. So, what does it mean? So, it's a good moment to recall what does it mean that for instance, What does it mean that G belongs to R0M? It means that G is a measure-up function and we can say that the measure, this measure, or the measure trace measure, it's the same of the set for which the density, we should choose a density. Yes, you remember that we can change the density on the set of the measure 0, trace measure 0. So we choose good spectral density such that for each t it's non-negative, for instance. It's enough for us. So when it's chosen, then it makes sense. The set I write this. So we take dm of t on f of t, and it should be 0 almost everywhere. Yes, so this set, when it's not 0, should have the measure equal to 0. Matrix measure or trace measure, it's the same. So this condition is not f but g. It was for g. So we assume this for f, and we ask this for f capital times f. So when we have this, just observe what would change. The question is, what is this? No, but this was the scalar for each term. So, and this was linear operator. So we can take like this, and this is just f of t, dm of t, f of t. So on the for almost all t, it was 0. So it will be also 0. So it's true. And this, you can, of course, now could think about some generalizations of multiplication operators, and you could think what we can make more in those spaces than only multiply by functions, scalar functions. For instance, we could consider also some interesting operators also for some other functions, not like this, when these are scalars, but also taking some matrices. So if it's for each t, it will be f of t would be a matrix. It will be not so easy to obtain the properly defined operator. You see this. For instance, but for some classes of matrix function, it works. If we have the commutativity, yes, we can make the same formula. But here we consider only scalar functions. Okay, so it means that our operator is properly defined. And now, when it's properly defined, I will write a long theorem about important spectral and not only spectral properties of this kind of operators. But first, I would like to recall the notion which is well known for measures and which is in some sense the analogic for matrix measure. This is the notion of, it's from French, I think, valeur essentielle, essential value, but the notation is from France, French, so we write this like this. V E M, because the measure is M now, of F. What is this? So this is a subset of complex numbers, and it is equal to C minus something which we call valeur non-essentielle. Yes, so V N M F, and this is, what is this? This set is the union of all such open subset of C, open. This means that it's contained in C and is open, okay? So we consider all open subset of C such that the measure of inverse inverse image of U by F is 0. And observe that this is in fact not something new, because this condition that this is 0 is equivalent to the condition that the trace measure of this set is 0. And trace measure, this is just measure. So we can say that this is the same what the analogic set for just trace measure, which is well known, and then we call this, we denote this also like this. So we can, in some sense, forget about this definition for matrix measures in this moment, and we can just think about the well-known notion of essential values for functions with respect to the measure. What is this? How to think about this set? It's something we can say that it's kind of an ansatz of, it's something which is not far from, usually not far from just the image of the function, but it's something which is not far from this, but which is, we can say, an ansatz of this set for all the values of F which are in some sense important topologically for the measure, matrix measure M, or this measure. Yes, and for instance, one of the properties which is quite easy to check is that this set of those values is always contained in the closure of the image. And sometimes it's equal for some kind of measures. It depends on several properties. Sometimes it's for when the measure is related to a topology and the function is continuous, then it happens that it's just the same. Yes. Okay, so this is just to think what is this, to understand what is this. Okay, but what we showed this is that it's the same essential values of M by M of F and essential value by M by trace M of F. Yes, this is just the same set. Okay, so it was, you can say the notation. And one remark, one important remark. Okay, so this is the union of open sets, of all open sets. And this union, of course, is usually uncountable. Yes, it's not countable union. And our measure is countably additive only. But this set is open set. It's even not important. But this is a subset of, this is, we can say, subset of complex numbers. So this is separable, and this is a metric space. So it possesses Lindelof property, which means that from any covering, we can every time choose a countable finite subcovering. So it means that not only all these sets have measure 0, but also the whole set have measure 0. It's important. So the measure M or trace M of this set, of the set non-essential values, yes, we can say, is also 0. So it belongs to those. It's one of those sets also, because it's also open. Yes. So this is the maxima. So we can say that the family of all those sets possess the biggest one, and this is the biggest. So we can define this also as the biggest open subset which possesses this property. Yes, it's convenient. Okay. So now the long theorem. I will not prove this because this is almost the same what we have for L2 spaces for the measure, but I should formulate it. So I think I will use this blackboard. So, assume that we have two functions, f and g. Most of the assertion will be for one of them, but sometimes we need two. These are measurable functions, scalar functions. Yes. Then first point Tf is densely defined and closed. Point 2. Oh, this is just multiplication for any lambda which is not 0, for any number, non-zero number, t of lambda f equals to lambda t of the f, and no, for 0 it can be different because this would be 0, so the domain is different, can be different. T0 always equals to just to the zero operator, yes. And 0 times Tf sometimes is defined on the domain of this operator. So
Excuse me, f is finite almost everywhere, yeah?
f, no,
Yes.
no, f is everywhere finite.
Everywhere finite, yeah. Okay.
F is just from omega to C, so it's defined everywhere.
Infinity is excluded, yeah? Infinity is excluded.
Yes, it's
Okay.
excluded. Of course, it's not very important, but because as you will see what is important soon, when I will compare two TF operators, yes, you will see that it's quite simple, but in a moment it will be just in the point 3. Okay, first part of point 3 is that TF equals to 0 operator if and only if essential value of f, we can write it's contained in one point set 0. Yes. I wrote this, of course, there are two possibilities. It can be empty, but it is empty only when the space L2 is 0 space. So this is quite trivial situation, but it can happen, of course. Yes. And the second part is answers your question in some sense. Tf equals Tg if and only if, and this is simple, just f of t equal g of t for trace m almost each t belonging to omega. Okay, I could write this here m, but by tradition we use this usually this notation for measures, not for matrix measures. So it means that it's not important. We can change values of the function on a set which has 0 measure. This measure is yes, and then nothing change for the operator. So it was to know that this is big difference between such equality and the equality for classes. When we wanted this, another condition was important. Condition which was related with the kernel of the spectral matrix measure density. Yes. So this is simpler in some sense. It's typical. It's typical for us. It's nothing strange. Yes. So this is another kind of condition. Okay, number 4. The question is, what are the conditions to be bounded operator? And it is like for operator of multiplication in L2 spaces for the measure. So it belongs to bounded operators in our space if and only if this set of essential values is bounded. Moreover, when this is the case. Then the norm of the operator is just the supremum of the absolute values. Yes, we can just write like this. This is the supremum of the set of absolute values. I will write this like absolute values of the set, okay? Which means the set of all absolute values of the sets. From the set. But we need here the condition provided that this is not a trivial space, because for trivial space the norm just is not defined. Does not have sense, because the unit sphere is empty in such cases. And now, starting from now, I think, no, later, point 5, the adjoint operator for Tf is just Tf conjugated, yes, thank you. I forget every time the name conjugated in English. Okay, so when we take F conjugated, it's just the adjoint, we obtain the adjoint operator. In particular, the domains are equal. Oh, this is just, when we have this is obvious, because it's obvious that the domains for such and such functions are the same. Yes. Point 6 is about the multiplication of functions and of operators. So, when we would like to multiply the operators, unbounded operators usually, what we get? We obtain a similar condition as for functional calculus for self-adjoint operators, or normal operators also. So it's contained only, and we can just compute the domain of this smaller operator. The domain of this smaller operator is like this. It equals to the intersection of the domain, this domain, yes, with the domain of the first one. In particular, we have the equality if and only if dt if times g is contained in the domain of Tg. Yes. And the next 4 points, for the next 4 points we should assume this extra assumption that the space is not trivial. If, moreover, our space is not trivial, then point 7, the spectrum of TF is just the set of absolute essential values with respect to m of the function f, which is the same, as you remember, as analogic set with respect to the trace measure. The point 8 may be here about the point spectrum. The point spectrum, which is the set of proper values or eigenvalues. It's also like for multiplication operators in L2 spaces for usual measures. So this is the set of those lambdas, complex lambdas, that the measure of trace measure m of the inverse image of the singleton lambda has non-zero measure. So this measure is not equal to 0. It's non-zero. Yes, this is the point spectrum. And point 9. If lambda 0 belongs to the resolvent set, now we know what is resolvent set. The resolvent set is the set of values, non-essential values. Yes, this upper set we use to define this set. So this is just the resolvent set. When we take lambda 0 from the resolvent set, then we can write that the resolvent operator TF minus lambda 0 times identity operator and the inverse operator is equal to TH, so it's also the multiplication operator by a function h, where h is a function omega from omega to c. It's any measurable function such that we can guess what it should be. Yes, it should be something like f minus lambda and 1 over f minus lambda. Yes, something like that. But of course, sometimes f has various lambda 0, so it should be like this everywhere. So we can write that the condition h of t times f of t minus lambda 0 equals to 1 for trace of m almost each t in omega. Yes? And now the last point, maybe most important for us, is about the spectral measure for these operators. What is the spectral measure? So let me recall, when we have operator A in a Hilbert space H, which is self-adjoint. So notation was like this, that EA, this is a function on Borel subset of R into projections, orthogonal projections, in particular in bounded operators in Hilbert space, but in fact each value of this is an orthogonal projection, and this is the spectral measure for A, the unique one spectral measure for A, or sometimes we call this spectral resolution or resolution of identity for A, in sense of the orthonormal projections. Yes. So using this notation, we can write like this. Now, first, we should know that we have a self-adjoint operator. So we shall consider in this point only the functions which are real. So if f is f of omega is contained in the real line, so then by the point maybe 5, yes, by point 5 it's self-adjoint, yes, and then when we want to take the spectral measure of this operator, for an omega which is Borel, for any omega which is Borel set, Borel B. This is equal to, and what should I write? I should write this here also, the multiplication operator, by the characteristic function of the inverse image of omega by f. Yes, it was something from, we can look here, f is from omega to r, so here I have a Borel subset, inverse image belongs to M sigma algebra, because it was measure up function, and now we have here a subset of measure up subset of omega. So this characteristic function is a function on omega which is measurable, and this has sense. And this is easy to see that this is of course bounded operator, and this is a projection, because those why this is a projection, we can see this for instance from this condition, and of course this is self-adjoint projection, so it's orthonormal projection because of the point 5, yes. So this is true, yes, and this is the end of the theorem, and the question is how to prove this. So I prepared the proof, it's in this manuscript I told you about, but in most parts the proof is almost the same like for L2 for the measure. In some parts it's delicate and you can find some problems related to this matrix measure, but in most parts it's easy. Maybe the last point is in some parts more technical, yes. But for instance, to prove that this forms, this is a spectral measure, not for this operator, but a spectral measure, it's almost trivial by those computations. So this is a spectral measure, it's just a simple calculation. But then to check that this is the spectral measure of this operator, it's something to do, yes, it's true, it's not completely trivial, but it's not very difficult. You should work somewhat with complex measure, because as you remember, the definition, what should be checked when you want to prove that that this is you have a spectral measure and you have the spectral measure E, and you want to check that this is the spectral measure of the concrete operator A. So you should check that the spectral integral of the identity function x with respect to this spectral measure is equal to A. Yes, it is something to check, and to check this, you should know what is the definition of such spectrum, and the definition is, this is a weak definition. This is a weak integral, so it means that we should take any x from the domain, so any x from the Hilbert space, such which satisfies the condition that it's even better, because it's enough to check this or this, because we every time know that in this situation this is self-adjoint and this is every time self-adjoint, because we have the real function. Yes. So to prove the equality of two self-adjoint operators, it's enough to prove that we have an inclusion. So for instance, we can take x from the domain of this or domain of this, and then to prove that it belongs to the domain of the second, and then to check that when we compute what we should compute something like this, then we take the complex measure which are obtained by taking something like this, also obtained by the definition is just the complex measure which is obtained by E and the scalar product in the obvious way. Yes, and by the definition of spectral measure, this is complex measure, and we should take something like this. So I'm sorry, here there's nothing, and on the right hand side we have A, X, Y, and Y should be it should be checked for any Y, and X should be from the domain. We should choose this domain, or this domain, and we should every time we must prove every time that it belongs also to the domain of the second one. So in this proof we make this from the left hand side. Yes. and we proved that it belongs to this domain. But it's technical, very technical, and long. You can check it. So I think it's a good moment to make a break.
Thank you very much. Okay.